Welcome to this session on distributed process management. In this session, we will cover the concepts of process migration and load balancing in distributed systems. We will also touch upon various load balancing algorithms, challenges, and their corresponding solutions. Let's understand what distributed process management is. It involves the coordination of processes across multiple computers within a network. This helps in efficient utilization of resources across distributed systems. It aims to provide transparency to users and applications, allowing them to operate as if they are on a single system. Distributed process management handles process creation, execution, and termination across different nodes in the system. The primary goals include improving performance through parallel execution, increasing reliability through redundancy, balancing the workload across computing resources, and ensuring efficient utilization of the entire system's resources. Here is an overview of process migration. Process migration involves moving a process from one node, usually an overloaded one, to another which is underutilized. Consider a scenario where we have an overloaded node with processes A, B, C, and D, and its CPU usage is at 90%. Process D is selected for migration to an underutilized node. After the migration, the underutilized node, which already has processes E and F, now takes on process D. The CPU usage on this node is only at 30%. This migration helps balance the load across the nodes, improving overall system performance. Let's examine the process migration mechanisms. Migration components include the process state, which comprises registers, stack, and heap, the address space, consisting of code and data segments, communication channels, which include open connections, resource access, such as files and devices, and process identity, including PIDs and user context. The migration process involves several steps. First, the process is frozen or suspended. Next, the process state is extracted. This state is then transferred to the destination node. The process is recreated on the target node using the transferred state. Finally, the process execution is resumed. Here is a simplified process migration pseudocode. First, freeze the process using the process ID. Then, extract the state from the process ID. Send the state to the target node. Recreate the process using the state and store it in a new process ID. Then resume the process with the new process ID. The process migration lifecycle involves several key stages. First, there is selection, where a process is chosen for migration based on factors like size, priority, and resource needs. Next is suspension, where the selected process is frozen to prepare for state extraction. The third stage is state capture, which involves extracting the memory, registers, and resource information of the process. After state capture, the state is transferred securely to the destination node. Finally, the process is restored by recreating it and resuming execution on the destination node. Note that this process also involves several challenges, including network latency, resource dependencies, and the need to maintain state consistency. Let's explore load balancing strategies, which are primarily divided into static and dynamic approaches. Static load balancing involves strategies that do not consider the current system load. One such strategy is round-robin, which distributes processes in a circular order. Another approach is weighted distribution, where processes are assigned based on predetermined node capacities. Task partitioning divides workload based on data or functional decomposition. Here is the pseudocode for a static round-robin assignment. For each process, assign it to a node by cycling through the available nodes. Dynamic load balancing, on the other hand, adjusts to the current system load. Load-based balancing involves migrating processes from heavily loaded nodes to lightly loaded ones. Threshold-based balancing triggers migration when load exceeds or falls below predefined thresholds. Predictive balancing uses historical data to anticipate future load patterns. Here is the pseudocode for dynamic threshold-based balancing. For each node, if the node load is greater than 0.8, Find the least loaded node among the nodes and migrate the process to the target node. Let's discuss the sender-initiated load balancing algorithm. Step 1. An overloaded node detects that its high load threshold has been exceeded. Step 2. It sends probe messages to find underloaded nodes. Step 3. It receives responses with the current load information from potential target nodes. Step 4. It selects the most suitable target node with the lowest load. Step 5. It initiates process migration to the selected node. Here is the pseudocode for the sender-initiated load balancing algorithm. The function sender-initiated balancing takes the current node as input. If the current node load is greater than the high threshold, then candidates send probe messages to other nodes. The target node is selected as the lowest load among the candidates. If a target node exists and the target node load is less than the low threshold, the process to migrate is selected from the current node and migrate that process to the target node. This algorithm works best in lightly to moderately loaded systems, but probe messages can add communication overhead, and it may cause process thrashing if thresholds are poorly set. Let's delve into the receiver-initiated load balancing algorithm. Step 1. An underloaded node detects that its load is below a low threshold. Step 2. It sends work request messages to other nodes. Step 3. Overloaded nodes respond with their availability to donate work. Step 4. The underloaded node selects a donor node with the highest load. Step 5. It requests a process migration from the selected donor. Here is the pseudocode for the receiver-initiated load balancing algorithm. The function receiver-initiated balancing takes the current node as input. If the current node load is less than the low threshold, the candidates are chosen from the send work requests to other nodes. Donor node is chosen as the highest load among the candidates. If the donor node exists and the donor node load is greater than the high threshold, then request a process migration from the donor node to the current node. This algorithm performs better in heavily loaded systems and reduces wasted migration attempts. However, it may have a delayed response in rapidly changing environments. Let's discuss the challenges and solutions in process migration. Key challenges include migration overhead. Transferring a process consumes network bandwidth and CPU resources. Processes may also have local dependencies that are difficult to migrate. Ensuring process state remains consistent during migration is crucial. Also, deciding when and which processes to migrate can be complex. Practical solutions to these challenges include conducting a cost-benefit analysis to migrate only when the benefits outweigh the overhead costs, maintaining proxies for resources that cannot be migrated to handle residual dependencies, checkpointing to capture consistent process state at well-defined points, and using adaptive algorithms that adjust to system conditions. Let's look at real-world applications of distributed process management. In cloud computing, it enables dynamic resource allocation to optimize VM placement and workload distribution, which leads to cost efficiency, elasticity, and high availability. For web services, it allows load balancing across web server clusters to handle traffic spikes and ensure consistent response times, providing scalability, fault tolerance, and improved performance. In high-performance computing, it distributes computational tasks across supercomputer nodes for scientific simulations and data analysis, enabling parallel processing, better resource utilization, and faster results. For mobile edge computing, it offloads computation from mobile devices to edge servers to save battery and improve response time, which results in energy efficiency, reduced latency, and enhanced user experience. In conclusion, process migration and load balancing are essential techniques in distributed systems that facilitate efficient resource utilization, improved performance, and enhanced reliability. As computing continues to evolve toward more distributed architectures, these mechanisms will remain critical for managing complex workloads across heterogeneous environments. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.